to see you all here. The SOC and the LOC did a very, very good job to prepare all this. So the stage is set. Now it's up to you to make a very nice conference. If it wants to. The first one. Yes. Okay, forget it. What I wanted to say. Okay, so perhaps I will tell you after the coffee break a few information about the excursion in Tulum and all these kind of things. Please, people who have a talk, bring your PowerPoint or PDF or whatever to this place 15 minutes before the session starts, or within during the coffee break, just before the session. Okay, so now a few words from also.
Just a very quick encouragement and invitation to everybody. I will have at the end of this conference to provide a summary. And so for my benefit, but also for the benefit of everybody, I invite those of you, those in particular who have talks that make specific points, something very difficult that you've been doing for the last 2 years of your PhD, such as getting the difficult titanium abundance, or something like this. I invite those of you to try and make the connections with the bigger picture. This is helpful in proposals, of course, it's helpful whenever you talk to your colleagues, but it's also going to be helpful for me in seeing you guys making the connection explicitly for everybody. And remember, we're here at conferences because we want to make these connections, the connections that are harder to make at home when you read a paper. So try and be really thinking hard about how your work, your specific area, connects to the bigger pictures, to the scenarios, to the models. And I think it'll really be helpful for everybody.
I'm Bruce Ballot. I welcome you to this APN 6. I'm about to do something that Christoph doesn't want me to do, so don't tell him. I would like Christoph and the LOC to please stand up. The LOC. Where's Miriam? Miriam, where? Stand up. Thank you all. A well-planned meeting. Everything has been working beautifully, and I'm just amazed at how inexpensive the meeting has turned out to be. That takes a lot of planning, and you've done it very, very well. Thank you for all of this. Now, this is APN 6. So would the 6 timers please stand up? 6 timers. So these are the senior people, they know everything. With the 5 timers, raise their hands. Great, great. And with the first timers, please stand up. Stand up. So you are, especially if you're a student, but even if you're not, take yourself very seriously. You're the future of this field. Wander around and talk to people. No one in this room will turn you away. So be inquisitive and push. The opportunities are out there, and this is a field which, as we'll be seeing, is full of some very exciting changes that are taking place. Yeah, let's see. I think that's it. Oh, no, one more thing. There's some people missing in action. So, although they have registered, they were not able to come, usually at the last minute. Romano was someone that we'll all miss. Valter. I'm just mentioning a few names that I happen to know. There may be others. One person whose name I would like to bring to your attention is Ervan Terzian, who has been in this field just about forever, at least since I was born. He was my thesis advisor, and he's undergoing a major operation right now. So he had signed up for the meeting but couldn't come. And I'm going to have a card for you to sign sometime later in the conference. Now, the first speaker, and someone whose talk is going to justify the entire registration cost. Introduction Sahai.
Well, that is a pretty intimidating thing.
So, I think if you connect this screen, this is not going. Okay, so welcome everybody. My personal welcome, and I hope it stopped raining outside. It was raining all night yesterday. I was not sure I would make it to the conference room without getting very wet. But here we are. Maybe the sun will start shining soon. It's certainly shining inside here, I think, with all these bright young faces here. Good to see all of you. So anyway, thanks very much to the organizers for giving me the honor to give this beginning talk. And I hope I can do some justice to it being the opening talk. So what I do is to try and chart the journey from an AGB star to asymmetric planetary nebula. And of course there's an amazing amount of observation work which has happened over the years, certainly the past 5 years, 10 years, which is just incredible. And I started making my talk, and I had very quickly 60, 70, 80 slides. I said, "Well, I can't do this. I have only 40 minutes here." So I had to cut and choose and pick. And so a lot of people's names might not be mentioned, work might not be mentioned. Please don't get offended. It's just we have a limited amount of time, and I'm just trying to give you an idea of what is in store for you with all the wonderful talks which will follow my talk. So the background, what are these extraordinary deaths of very ordinary stars that we all want to understand? And we begin the journey by looking at imaging surveys, that is the morphologies from AGB stars to pre-planetary nebulae. We try to understand the mass loss phenomena which are happening during these phases, and how things go from spherical symmetry to aspherical symmetry. The focus will be very strongly on the early phases here, because I think that's where all the action happens. I'll be discussing extended envelopes, lobes, central regions, and I will try to go from larger scales to smaller scales, but that won't always be possible because some observational techniques, of course, refer both to large and small scales, like, for example, millimeter interferometry. So I will be discussing specific studies, and these will highlight the different observation techniques, including far-infrared observations, observatories like Herschel, and of course the new breed of interferometers conducting very nice interferometric imaging in the millimeter, sub-millimeter wavelength range, X-ray observations, UV observations, and I'll end with a short summary. So here's something which I think even the youngest people here are pretty familiar with. This is the typical evolutionary track of a solar mass star, going over the RGB, and then going to the AGB phase where we have a central carbon oxygen degenerate core surrounded by helium and hydrogen shell. Most of the time, burning occurs in the helium shell, gives the luminosity to the star, and then every once in a while you get burning in the helium shell as well. You get these thermal pulses. The helium shell manufactures carbon, so stars go from the normal type, which is oxygen rich, S type, where the carbon oxygen ratio is which we want, to carbon to stars, where the oxygen to carbon oxygen ratio becomes greater than 1. And generally we understand, during this time, these stars, which are very cool, very luminous, very large, they have very dusty expanding envelopes. And these envelopes are expanding at low speeds, 5 to 20 kilometers a second, but they have very, very large mass loss rates. So in fact, because of these large mass loss rates, the evolution of the star is determined by the mass loss rate. So any star of the mass of the sun or more, which will go through these phases, has to lose half or more of its mass during this phase. And now, it's reasonably well understood that winds during this phase can be driven by radiation pressure and dust grains. The grains are driven out by radiation pressure that guide the gas along, and this requires that there should be rough equality between the radiative momentum available to mass loss rate multiplied by the expansion velocity. And this holds true for most of AGB stars. However, there are important exceptions, and one which I will discuss today is the Nebula. And that sort of tells us that we have to be trying to understand even the mass loss phase and the AGB phase better. So, what are these accelerators I'm going to talk about today? So, after most of the stellar envelope is lost to the mass loss, the mass loss ceases, of course. Here's a picture of RxC 10216. The Dutch shell sees scattered light. You can see this is very, very extended, about 200 arc seconds across. And you can see these spherical shells, which I'll also be talking about later. If you appear at the center of this object, this is just the image, and you can see this bipolar structure. There's a dense dust laying across here, and there are light going out in directions where there has to be dust. And here's a picture of the same central region in molecular gas. It's in, and you can see this. There's a torus here, which corresponds to this region. So there's a very, very dramatic transition which is occurring at the centers of these objects at a very late AGB phase or at the pre-planetary nebula phase. Here's a picture of pre-planetary nebula, the famous M nebula. You can see again these extended dusty envelope seen in scattered light. You see the circular arcs, you also see the searchlight beams, which are basically just illumination, preferential illumination from the central star, which has a dust mask around it. So, what happens? So, the morphology changes dramatically. The outflow velocities change dramatically as well, from 10 kilometers per second to 100 kilometers per second. So, now I'm going to continue my talk in a moment, but let me at this time just take a moment to say what happened from APN 1 to APN 6. So I basically, in my view, and maybe it's a very prejudiced view, we divide this era into two eras. One is pre-WIFPIC 2, that is a corrected HS2 optics, and post-HS2 WIFPIC. APN 1 was before that, and APN 2 and all the other APNs, and as well as fine APNs in Russia, which are now heavily focused also towards understanding this transition from spherical base to asymmetry, happened after that. And Adam Frank in APN 2 said the paradigm loss new theories were aspherical behavior. And I'd just like to read this out. It appeared that the needed theoretical interpretation had been found in the generalized interacting stellar base model. Now this is before. This model, in fact, is simply the hydrodynamical coordination of a fast wave of the central star of Planetary Nebula by pre-existing equatorially density enhanced aging down. After this, with the coming of WIFPIC 2 and the beautiful images which we got of Planetary Nebula, young Planetary Nebula, pre-Planetary Nebula, things changed dramatically. And Adam Frank said in the same paper, the new data indicate that the purely hydrodynamic interacting stellar base model cannot recover further shapes of kinematics. And I think that's understandable. I also want to, now, so where are we? Well, at APN 5, Joe Casper gave a nice conference summary, and one of the points which I took out from there, and which I think is still a grand challenge in front of us where we want to go, is to construct a detailed set of binary decision trees, as had been constructed by even to the call for superior type progenitors, that apply to both the Planetary Nebula and related objects. So that is sort of our dream, and once I think we realize this, we will have a very good understanding of what's going on. Now here is a list of all the topics. Maybe this is not even comprehensive of what I have not been able to do in my talk. And many of these, probably all of these are going to be covered in later talks in good detail. So without further ado, now let me continue. So what are the observations telling us about the AGB-PN transition so far? Well, the mechanisms that shape Planetary Nebula become operational significantly before the Planetary Nebula phase. That is the post-AGB phase and very late AGB phase. Now, very early on, Noam and Soper realized that the GISW1 could not explain the few Planetary Nebula that were known then, which had once contained very conical downflows, as an example. The HSC surveys, which I will describe in a moment, showed that the point symmetry is very widespread. Multipolar structures are seen very often, and collimated lobes are very seen often in young Planetary Nebula. And this, we use this survey to conclude that collimated fast wave objects operating during the pre-Planetary Nebula phase or very late AGB phase are in fact the primary agent for shaping most aspherical Planetary Nebula. Now, of course, there is a dense equatorial torus that may help in further confinement of fast outflows which occur later during the Planetary Nebula phase. So, and In addition, the morphological data suggests, especially for example, point symmetry and the presence of ANSYM, that the winds and the jets are collimated as they are launched. They are not hydrodynamic. Hydrodynamical collimation may play a role, but that is not the primary collimation agent. Now further on, after the pre-Planetary nebula evolves to the young Planetary nebula phase, you have the action of the very fast radiative wave, the SRFW as I call it, which of course then acts on everything else which has already occurred. Another important thing to note is in this paper that Laura was that these very fast molecular bipolar outflows which you see in pre-Planetary nebulae, they have very, very large momentum excesses, and it's quite clear that these winds cannot be radiatively driven. Okay, so there are, of course, a number of fundamental questions. So what are the factors of going into mass loss rates, starting in the phase? What factors decide if the AGB object becomes a pre-Planetary nebula, or what I call, I described at the moment, a disk-prominent AGB star, or AGB pre-Planetary nebula, which I also described. What are the origin and properties of these fast outflows? What is the nature of the jet engine? What is the origin and properties of these equatorially dense structures? That is, the waves, are they bound or are they expanding? At least in one case, we know it is bound. And its binarity, of course, that's the million-dollar question. Binarity is the underlying cause of the radiant symmetry. And I think if I took a poll right now and asked people to raise hands, I think a lot of people, the majority of people would believe that binarity is really. And of course, Soka and Ursula have done a lot of work in supporting this view, and other people as well. My figure is not showing here. I hope that's not the result for other things as well. So now, are magnetic fields responsible? I'm not going to talk too much about them because there is a review talk to follow in this session. But I will just point out that one of the problems which has been with magnetic fields is that they've been measured using masons. And masons, of course, are very localized phenomena, so it's never been clear whether these fields are really local or global. However, now there's a very nice paper on Atari where polarization of thermal lines has been detected and by Mono Lemmings et al. And they concluded the fact that we're seeing global magnetic fields, so that is very exciting. This is a figure of W43A, which is what found in the glass of very high glass outflows. And this paper shows a nice measurement of magnetic fields, laser spots of this object on its jet outflow axis. So, 3 morphologically unbiased HSC surveys using very rather simple selection criteria have observationally bracketed the evolutionary phase over which the transition occurs. And so, this is the way it went historically. Of course, I'm going to go in the other direction that I described. So, we did a survey pattern and was simply selected by them being compact and low excitation. Then we carried out the pre-Planetary nebula survey. Again, we selected stars with heavy mass loss rates and also requiring that the RS F25 to F12 ratios greater than 1.4, which indicates the lack of hot gases, implies that the heavy mass loss is stopped. And so these objects are very low pre-Planetary nebula. And then survey of nascent pre-Planetary nebula. These were also they're actually AGB stars, but the 25-12 micron ratio is slightly smaller. So, but still greater than what you would expect for still continuously using mass loss. We're talking this ratio should be about 0.5 less. So, before I describe them, let me also mention that there are other categories of post-AGB or PPM-like objects which are also important for our study. And these are the disk-prominent AGB objects. These are central stars or post-AGB spectral types. These are all radial velocity binaries, at least all of them which have been observed. And most or all of them observed mass lies in a certain binary disk. And there's little or no extended velocity. This is a lot of work done by Armstrong Infinix collaborators. And these objects may actually be almost as numerous as pre-Planetary nebula. Now there's a class of objects very rare, which I call AGB PPM. So these are the nebula look like pre-Planetary nebula, but the central star is still an AGB star. These are rare. And then of course there are this objects which have symbiotic stars in the center and have Planetary nebula like pre-Planetary nebula like around them. These are also rare objects. So here's our few results from the survey of nascent pre-Planetary nebulae. These are basically all AGB stars with heavy mass loss rates. I described selection criteria to you. And what you can see is that these are all, or at least, but out of the list of 45 objects that you imaged, 30% were resolved, and 60% of those showed asymmetrical structure. And most of the asymmetrical structure corresponds to elongations, polymetric elongations like this. Now, this is rather different from the nebulosities you will see from pre-planetary nebulae detection text. So these are a small mosaic of objects from a pre-planetary nebula survey, and you can see that these are pretty collimated. Quite a few of them are collimated, some with dense to base, multipolar objects, and for comparison, this is the base of one of the base of pre-planetary nebula. So you can see the difference in morphology between here and here. Now, these pre-planetary nebulae, I will show you, look very similar in the morphologies to young planetary. So there's a very strong connection between these objects, obviously. Now, this survey resulted in a detailed morphological classification scheme, which I described when I described young planetary nebulae, because the same scheme was then adapted to young planetary nebulae. So now I'm quickly going to run through a bunch of slides showing different morphological types for young planetary nebulae. Most of these classes, or at least 4 of them, are the same primary classes as for pre-planetary nebulae. Here's the primary class, which is bipolar objects. Bipolar objects require the base should be pinched in, the lobe should go in towards the